Math 1343, Week 8, Video 12, Test for Association, P-Value Approach. Again, the p-value approach is just a different way of doing hypothesis tests. I like to teach both because depending upon what your future studies entail, you may encounter the critical value approach or you may encounter the p-value approach. Both should give the same results though. Without restating the entire problem, we're still testing at alpha equals 1% if there is an association between gender and type of degree. And just a reminder about those steps for the p-value approach, how they're similar and different from the steps for the critical value approach. The first step is still the same, state the hypotheses. As a reminder, for a test for association, the null hypothesis is always there is not an association between, in this case, gender and degree type, and the alternative hypothesis is, yes, there is an association. The calculation of the test statistic occurred 2 videos ago, and we got a value of chi-squared equals 565.9662. But this is where the p-value approach deviates from the critical value approach. In the critical value approach, our second step would be to calculate the critical value and label the regions. In the p-value approach, we skip that, and then with the test statistic, we calculate the p-value. Again, the p-value can be interpreted one of 2 ways. The technical interpretation is the p-value is the probability that our sample occurred given that the null hypothesis was true. Visually, the p-value is the area of the tail cut off by the test statistic. This is still a right tail test. We still have 2 degrees of freedom using the same formula from before. And so our p-value would be the area of the right tail cut off by chi-squared equals 565.9662 with 2 degrees of freedom. Now the problem with the p-value is if we're using a table, then chances are we're not going to find that exact area because our table only has 10 specific areas, only 5 of which I've written up here. I've written the right tail areas. There are left tail areas, so to speak, or rather areas to the right of left tails, but these are the only ones that we need. To locate the p-value, we have to find a range of areas that the p-value could be based on our test statistic. In this case, 565.9662. Our chi-squared values are what we read across here. And chances are this number's not in there. So we try to find what 2 it's between. Well, this is a ridiculously large number. And as we go left to right, notice that the chi-squared values are getting larger. But by the time we reach the end of our table, where the column represents a right tail area of 0.5%, we're only at chi-squared equals 10.597. So what does that mean about our p-value? Well, the chi-squared we're looking for would be way over here somewhere, 565.9662. This isn't between anything, it's off the chart, literally. So what does that mean about the p-value? That means that the p-value would be somewhere down here, but what's happening to these areas as we move left to right? They're getting smaller and smaller and smaller and smaller and smaller, which means if we move off the chart, we would expect the p-value to be even smaller. So the only conclusion we can draw about the p-value is that it's going to be less than this last area. So we can conclude that the p-value is less than the smallest area in our chart. So that's all we can say about the p-value without resorting to technology. I would guess that the p-value is probably 0.00 and then 4 or 5 or 6 or 7 or 8 or 10 or 12 more zeros before you get to a non-zero digit. Kind of curious though, I'll look it up after the video. So now that we know our p-value is less than 0.005, we can move to our 4th step, which is to make a decision. And remember, in the p-value approach, your decision is made based on comparing to the p-value to the significance level. In this case, the p-value is really small, but it's clearly less than 1%. It should be pretty clear. but that's equal to the significance level. So since the p-value is less than alpha, we reject the null hypothesis, which we should have. It's what we did last time with the critical value approach. The significance level is like, all right, we'll accept up to a 1% chance of something happening, but if something happens with a smaller probability than that, your null hypothesis was high. Your null hypothesis was wrong. Our sample had less than a 0.5% chance of occurring, which is less than 1%, which is the significance level. So we reject the null hypothesis, accept the alternative in its place, and conclude there is an association. So the p-value approach, again, it's just a different way of answering the same question, but instead of having a critical value and comparing your test statistic to it, you take your test statistic, cut off the tail, come up with its area or a range for its area, and use that to compare to the significance level. Less than alpha, reject. Otherwise, do not reject. In the next and final video, we're going to do one more test for association, complete from the beginning to the end, but I'll make sure that the arithmetic is just a tad more manageable.